welcome to Humboldt University in Berlin. I'm happy to see so many of you here, so many familiar faces and so many new faces. So I hope you're all looking as forward to the talks as I am. But before we get started, I just want to briefly acknowledge the German Science Foundation, the DFG, the Foundation La Caixa, and the IGFAE in Santiago de Compostela for their financial support in organizing this event. Then some practical announcements. I'll try to keep this very brief. Please make sure that you all register and pick up your badge. This is important for our administration and, for example, for the conference dinner. If you have urgent questions or issues, please talk to one of the organizers or the conference secretary or one of my PhD students or something like this during the breaks. We all have these blue lanyards. Yeah. So for local issues, it's of course better to talk to local people. For general conference-related issues, you can talk to any of us. Right, so in terms of Corona, please all wear a mask if you can, and please do a self-test if you haven't done one. And in case you have symptoms, you can get both masks and tests for free at the registration desk. Then in terms of internet, if you have Eduroam, everything should work fine. If you do not have internet, Eduroam and you need to use the internet, please talk to me or Rob over here. Right, then coffee breaks, lunch and reception today will all take place outside here in the hall and outside here in front of the building. So there's seating outside as well. There should always be vegan and vegetarian options available. But during the coffee breaks, the vegan options beyond the fruit are kind of limited, so please don't take this unless you actually registered as being vegan. Right, then I'll say more practical things at the end of the day today, but now it's time for the first talk. So for this is my pleasure to introduce Arkady Tseytlin from Imperial College London, who will tell us about reproducing gauge theory free energies from the string side of ADS-CFT and how this can be quite subtle.
So it's a pleasure to be here in Berlin again, and I will start with somewhat mixed topic talk, which is a little bit out of the main theme of the conference, but at the same time it's kind of quite close and maybe will give some different perspective on some things. So what I'm going to talk about is based on several papers, and my talk will be, if I'll manage on time, will be having two parts. One will be about some n equal 2 models and their free energy as it follows from localization, and then the second part will be based on this last paper, most recent paper. Well, actually, there are two recent papers, but this one, the last one, which is about how we can understand this free energy from supergravity, at least the leading term in the free energy. So let me start from far away, and just to mention that we're coming close to 25th anniversary of ADS-CFT, and what we know so far, on one hand is quite a lot, on the other hand is limited, and what we understand more or less is how the duality works in the planar limit, and that is based on integrability. But if we go beyond planar limit, we face the questions of what happens with 1 over n corrections, and there are some other observables which one may also ask whether they are controlled by integrability. So just to set up the notation, this is a very familiar story. So for exact correspondence, we need to keep G string and string tension arbitrary, or the same as saying the J. Young-Mills and N of SUN group. But then we can consider Toft limit in which we expand at large n at fixed lambda, and then we can expand in large lambda, and that's the most obvious comparison which goes in when we look at strings, weak coupled strings, and try to take large lambda expansion on gauge side. So working out large lambda expansion direct on gauge side is a challenge, but for some particular observables that's possible, and that will be related to what I'm going to talk about. So again, starting from some general comments. So why we're interested in the integrability? So on one hand, if we have integrability, we can say something about string spectrum in curved backgrounds, particular special curved backgrounds. At least we hope that integrability allows us to find the spectrum of energies, and ADS spaces provide examples. On gauge side, integrability is present in at one loop order in all sorts of gauge theories, but beyond that, in N=4 theory, we have integrability at the leading order in large N expansion. So integrability controls a spectrum of anomalous dimensions and possibly some correlators. So it applies for any value of the parameters. So large N, but any value of gauge coupling. So what about finite N? And later on we'll also ask about less supersymmetric theories. So here we may hope that there are also other methods may be useful. In particular, localization applies in supersymmetric case, which could be N=2, possibly N=1, but it only applies to certain special observables. So it's kind of limited in scope, but it applies for any N and any lambda. And then there is also bootstrap, which is based on quite general principles, but it's not particularly useful to getting some explicit information apart from some bounds, and in some cases, the very sharp restriction on region of parameters. So there was some recent progress on combining these different methods, maybe combining even integrability and localization and bootstrap to gain some information about some particular correlators and trying to understand what would be their interpretation ADS as some scattering amplitudes in ADS, etc. So if you go back to IGST conference, you will see, for example, talk by Aldai discussing some of this. So if we try to go beyond N=4, so one simplest possible case is to consider certain orbifolds or antifolds of N=4 theory. And indeed, there are special N=2 superconformal theories which are planar equivalent to N=4. And these are the simplest examples to study. So they will be controlled by at least their untwisted sector will be controlled by integrability. They are planar equivalent to N=4. They will be integrable in that limit, just equivalent to N=4. But then one could ask what happens in twisted sector, or what happens when we go beyond the planar limit. What happens including 1/n corrections. And that will be the main topic of what I'm going to talk about. So in N=2 models, localization matrix model, so here localization applies, and it applies to particular observable, which I'll be discussing, which is free energy, which is essentially logarithm of partition function of a gauge theory defined on phosphere. So one could also discuss, there are closely related observables like BPS Wilson loop and also correlators of some chiral primaries, but I will focus only on free energy. So this free energy can be computed using localization matrix model. And it will be depending on N and gauge coupling. And then we can consider expansion at large lambda and try to see whether we can compare to string theory. So that's essentially the circle of ideas which I want to address. So the challenge would be really, there are two challenges. How to expand the result of localization matrix model at large lambda. This is a technical challenge, as will be clear later. But also technical and conceptual challenges, how to compute this on string side, this free energy, and to compare to localization result. Just to give some perspective on what I'm going to talk about, let's start with the simplest example, namely free energy in N=4 theory. So we consider N=4 theory defined on phosphere. And N=4 theory is finite, but if you define it in curved space, in general, there are ultraviolet divergence, which is controlled by conformal anomaly. So in the case of phosphere, this is just A coefficient of conformal anomaly proportional to dimension of the group. So the free energy is just this divergence. R is the radius over the phosphere, UV divergence plus some constant. And this constant clearly depends on the scheme because there is ultraviolet divergence. Depending how you subtract it, you can change this constant. So if you consider, so this is just from quantum field theory perspective, and that free energy doesn't depend on Toft coupling a priori because A is just, it's not randomized. So the constant may depend on lambda depending how we decide to define this object. Now, on localization side, we're dealing with Gaussian matrix model, in this case of N=4 theory, and assuming particular measure, which essentially is like a special scheme, and dropping divergence as it's done when defined in localization matrix model, one gets the following result. So essentially, one gets the same coefficient A, which is the dimension of the group, times logarithm of Toft coupling, lambda, plus a constant which is just function of n, which is related to dimension of SUN group. So that's the result which comes from localization matrix model. So this log lambda is may look strange, but it's some power of lambda in the partition function. So what would be the analog of that from on dual side? So from ADS CFT side, free energy should be matched to string partition function, first quantized string partition function on ADS5S5, which should be properly defined in the tree level, namely large n. That's two-sphere topology in string theory. This is essentially like supergravity action. There will be no alpha prime corrections in this case. This is just ADS5S5. It has maximal supersymmetric vacuum. So essentially, supergravity action, you look at supergravity action, and you conclude that it's proportional to the volume of ADS5. This step is not completely innocent, as I'll discuss in the second part of my talk. So why supergravity action is just a volume of ADS5 on ADS5S5 space. But let's assume that's the case. Then this volume is infrared divergent. If you introduce cutoff on the radial direction of ADS, you get log divergence proportional to the coefficient A, which is the same conformal anomaly coefficient, which is just proportional to n squared at leading order at supergravity level. And then if we decide to fix this infrared cutoff in ADS in a very special way, as was suggested by these authors, then one can match precisely this log lambda. So just picking up this infrared cutoff in such a way that it gives us just lambda, we get matching with this localization matrix model result. So this is a little bit ad hoc, and indeed why we should pick this particular cutoff, but there is some logic that this is natural in the case of ADS CFT if we want to match these expressions. As for -1, it comes from one loop effect, which is torus topology on the string side. So indeed, one could argue that computing one loop string correction, which in this case just boils down to one loop supergravity, one reproduces also this -1 in this expression, this one. So that's essentially how comparison should go, and one would like to generalize it to say n=2 models. So what do we know about these n=2 models? There are, in fact, very special, there are very few simplest superconformal models which are planar equivalent to n=4. And so that means they have simple ADS dual. And to find them is basically one needs to look at one loop beta function of gauge theory. So in n=2 case, beta function is just given by one loop coefficient. So if you take a SUN group, the simplest choice of representations is just some number of hypermultiplets in the joint, fundamental, rank 2 symmetric, rank 2 antisymmetric. So these are lowest dimension representations. If you go to high dimension representation, you will never manage to match beta function. So there are very few particular theories, and I will call one of them contains symmetric plus antisymmetric representations. So rank 2 symmetric, rank 2 antisymmetric, hypermultiplets, and another contains some number of fundamentals and antisymmetric. So I'll call them SA theory and FA theory. So SA has one symmetric, one antisymmetric, no fundamental multiplets. FA has 4 fundamentals and 2 antisymmetric. So these SA and FA models are essentially may be viewed as orbifold and identifold projections of N=4 theory, and they will be due to similar projections of AdS5S5. So again, to emphasize demanding conformal invariance and planar equivalence to N=4 selects very special theories for the simplest group SUN. And just to give an idea why they are planar equivalent, you can look at the conformal anomalies of these theories, and they all start with n squared. So in FA theory, which has fundamentals, there is also the difference comes in at order n. So n squared terms match with N=4 theory, but already at order n there is a difference in conformal anomalies. But conformal anomaly is just controlled by free theory, essentially. There's no interactions involved. Now, another very special theory is found when you take a group, we take a group SP to N. So here, conformal invariance condition, again, one loop beta function, selects particular theory, which is a FA model, again, fundamentals plus antisymmetric, but here we have 4 fundamentals and 1 antisymmetric to match the beta function. And similarly, this is the conformal anomaly again N=4. So N=4 has dimension of a joint is n times 2n plus 1. The group SP to n has this dimension. So it's essentially that's what appears in the A anomaly. But in N=2 theory, the second coefficient is different compared to that one. So what about localization matrix model? So in these N=2 models, we can apply localization. And just to recall what this localization is about, essentially we define N=2 model in a 4 sphere. This has to do with regularizing infrared divergences. The way how this is done was done by Pistun. It's a kind of special way of defining both the measure and the integrand. So that corresponds to a particular scheme in this language of which I mentioned earlier. So what localization is about? The claim is that path integral of gauge theory is reduced to integral over one constant scalar mode. There are 6 scalars in, there are not 6 scalars. There are N=2 vector multiplet in the case of N=2 coupled to hypermultiplet. So in N=2 vector multiplet, there are scalars. So you could pick up one scalar. So this scalar, or in N=4 language, that will be the scalar of one of the 6 scalars of N=4. So this scalar has an action which comes just from very special terms in the N=4 theory defined on the 4th sphere. In particular, there is a term where you have a scalar coupled to R6, so this conformal coupling of a scalar on curved space. So for sphere, curvature is non-zero. So you get, from this term, you get trace A squared term. So A is a constant mode of this scalar phi. So it's essentially, in SUN case, a joint matrix. Not a joint, Hermitian matrix A. So the expression which is written here, there is some measure of integrating over A. The free action comes from that term, essentially, plus some other term, but it's basically proportional to gauge coupling, 1 over G Young-Mills, or lambda over n, times this trace A squared. And there is a one loop term, or interacting part of this action of matrix model, which I'll describe on next slide, but in N=4 theory, there is no this term. So that's essentially the measure, the action. So if you do the integration, it's like Gaussian matrix model. It just gives us this coefficient in power how many matrices you have. So it's essentially dimension of the group. And with some normalization on the volume of the gauge group, that gives this prefactors here. So that's how this formula comes out of localization matrix model. So free energy is just logarithm of Z is just logarithm of lambda times dimension of the group. Now, in the N=2 models, with some number of hypers and some representations, if we consider large n expansion, we can ignore instantons. And then the expression for this integrand in the matrix model is just a ratio of determinants, one-loop determinants. So you just take n equal 2 or n equal 4 model, you expand it in this constant A background, and consider one-loop fluctuations. And these are these determinants. I'm not going to explain in detail, but it's essentially determinants of Laplacians with mass terms, which are determined by this constant A, on a 4 sphere. So it's an infinite product over modes, and you need to regularize it. That's essentially what gives this log divergence in general, but if you regularize it in a certain way, you end up with this particular expression for this one loop term, which determines the interaction part of the action of the matrix model. So what appears here is a product of two, what's called Barnes function. It's essentially a function which satisfies this relation with gamma function. So if you shift the argument by 1, you get multiplication by gamma. It's an infinite product of some sort. I will show you more explicitly. But essentially, the one-loop term in the matrix model determining interaction part of the action is given by some special function, which is a kind of infinite product. So that's what one should take of this. So in these n equal 2 models, explicitly we can just write everything in terms of eigenvalues of the matrix A. So that will be a path integral like this with a particular measure, one Demont determinant, etc. But what is important, so this is what's important where Young-Mills coupling is, so lambda over n. It only comes here in in S0, as interaction term doesn't depend on gauge coupling. It's just these one loop determinants, they depend only on A. And this interaction part, that's how it looks like. So this H matrix, it's essentially this infinite product. So here it's redefined a little bit. So depending on number of multiplets, the interaction part contains various terms of log H with different arguments. Again, AR are eigenvalues of this matrix A. So this H is this product, and a logarithm of H has a very simple form. Well, simple sum. So log of H of this function is just powers of x, the argument, with coefficient, which is values of Riemann zeta function times this prefactor. So what one needs to do, one needs to pick up particular model and then sum up these interaction terms, and that will be infinite number of terms. So it's kind of complicated interaction term. And that's explicitly how they look like for particular models. So for SA model, which has equal number of symmetric and antisymmetric, after redefining A like this by lambda, so that kinetic term is just Gaussian without any coupling, the coupling appears in the interaction term now as lambda in some powers. And in this SA model, we just get double trace interactions. And that means this H depends on both the eigenvalues. And these are coefficients which appear. Again, some values of zeta functions, gamma factorials, etc. So that's very explicit, but quite complicated. So the moral of this is that if you want to develop perturbation theory in lambda, this is straightforward. It's just powers of lambda appearing in interaction terms. You can do integral over A to any given order in A. In lambda, you just expand in lambda. But what if you want to know large lambda expansion? And that's a challenge, because somehow we need to understand how to do large lambda expansion here. For any finite n. So n, I'm not touching n so far. I'm just assuming we will be also expanding 1 over n, because we dropped instantons. So what we want to compute is free energy. And the first leading term in free energy will be, again, Young-Mills term, planar equivalent theory. So this interaction will go away at least this order. But if we take a difference between this, say, free energy of this SA model and Young-Mills, that will be 1 over n squared correction, leading 1 over n squared correction. And that's what we'll be interested in. So we normalize essentially to that super Young-Mills, and would like to find how this delta F will look like at large lambda. So similar story explicitly for FA model with fundamentals and 1 over 2 antisymmetric. So here the interaction term contains extra term, so similar double trace term as before, as in the previous theory, but there's also single trace term. With coefficient, again, there's some zeta function. So So here, because of this single trace term, or because of the fundamentals present, there is the delta f, the difference with super-Young-Mills, starts with order n term. So previously it was just order n squared term, or order n in power 1. So the leading term goes as n squared, Young-Mills goes as n squared, subleading term goes as just with n in power 0. So here, in addition, there is term in of order n. So if we finally go to SP model, this is actually the simplest model for which one can get quite explicit expressions. So it turns out this SP to n model with with 4 fundamentals, 1 antisymmetric, is the simplest model. In this case, interaction term has just single trace interactions. And here one could work out quite explicitly what are these terms in 1 over n expansion in free energy for any lambda. So the leading term F1 is essentially an integral of Bessel's with lambda entering like this as argument of J1. So you can do this integral that way or another and work out what's lambda, large lambda expansion. So again, small lambda expansion is straightforward, but large lambda needs some work, and that's what we get if we do this. We get term over the lambda, log lambda, some constant. A is some glacier constant, but what's important, then there's 1 over lambda term and then nothing. And then there are exponential corrections. So they just follow from this integral. And all terms like F2, F3, etc., they're all determined by this F1 through derivatives or integrals. So they're all related to F1. That's a claim that follows from this structure of this matrix model. So essentially, knowing this and taking derivatives and integrals, etc., you can work out the whole series. So what happens to be exact result is has the following structure. So the free energy is just n squared plus n. So n squared is again will be n equal 4 theory with group S2Pn, and n squared plus n plus constant log lambda. I'll explain what lambda prime in a second. Then constant, then term 1 over lambda, and then exponential corrections. So lambda prime here is redefined lambda. It corresponds to shifting Young-Mills coupling by a constant, log 2. It happens that it looks like a scheme change, but indeed this is kind of encoded in the structure of this matrix model that there is this shift. And this shift resums all sorts of terms with log 2, which appears as subleading order. So in principle, that's an explicit expression, so we'd like to match this to string theory. So that's essentially the main aim. So let me quickly say what is known about other models. So again, SP2N model is the simplest, but in other models can also say something about at least leading 1 over n squared correction to free energy. So structurally the simplest is orbifold model, which essentially is just quiver with equal couplings. So SUN with two adjoint two B fundamental multiplets, which connect these two groups. So this is just essentially can be thought of as an orbifold of n equal 2, n equal 4 theory. It's planar equivalent to n equal 4. It's dual to orbifold on the string side. And what is important for me here is that we can work out the strong coupling expansion of the free energy in this case using particular form of this correction to free energy, which follows from matrix model. So matrix model, one can show that delta F, then namely the 1 over n squared correction to free energy, is determined by logarithm determinant of semi-infinite matrix. Just particular matrix, which is integral of product of two Bessels, like this. There are two of them, m plus, m minus. So obviously these are integrals which you can expand in small lambda, and then you get the result in a series of lambda. But at large lambda you can also expand them, but that's not legitimate because we're supposed to do infinite product, infinite determinant first. So it's actually non-trivial how to work out the strong coupling expansion. Interestingly, the precisely similar, well, quite similar expressions like log determinant of some semi-infinite matrix appears in a different context, what's called octagon correlator. in NeCo4 theory. It's a particular correlate of large R charge, 4 BPS operators with large R charge, scale to infinity. So in this case, it was understood how to work out this correlator for particular values of x. Well, I'm not going to discuss details. All I want to say is that similar object appears there. And using this technique, we recently understood how to find strong coupling expansion also for this case. And what one finds is that this orbifold theory, free energy goes like this. So again, it contains log lambda, but it also has square root of lambda as a first term, then there's some constant, and then series of terms 1 over lambda. Here, lambda prime is different. It's redefinition of lambda itself by log 2. So the series here, which is written here, there is I here. So that indicates this is just particular way to defining this infinite sum. The sum is not convergent, not Borel summable, and here these non-perturbative corrections are kind of imaginary. These are all details. I'm not going to discuss non-perturbative corrections. What is important is that the structure of this series is, in all these cases, is consistent with what you would expect from string side, namely expansion alpha prime 1 over square root of lambda. So this, again, to summarize, the free energy expanded at large n is having this kind of series expansion. Why square root of lambda? We will need to understand why it starts like that. There's no good reason, but a similar structure is precisely for this octagon, where the square root of lambda was. So again, octagon is like partition function, it's exponent of f. So there is a square root of lambda in exponent, and then that suggests some semi-classical string interpretation. It will not apply here. It has nothing to do with minimal surface, etc. But interestingly, it has similar structure. Just to say that in this other model, I say similar story applies. Again, the planar correction has log determinant expression, and essentially a similar series is found also here. So this orbifold theory, SUN, SUN, and SA model is very similar. FA model is kind of a cross between SP2N model with fundamentals and this SA model. It has also order n term, and then there are other terms which contain similar corrections. And here, F1 is essentially the same as SP2N model. So these are all details. Let me quickly say something about dual string interpretation. So for orbifold theory, I already mentioned this is just orbifold of ADS5, S5. This is old story. Particular Z2 orbifold. And in principle, I'm going to ask what will get computing string partition function in this case. For SA model, there is an orientifold involved as well. And there's a particular way to define which orientifold we should take to get the dual theory. The logic here is you need to kind of first start with flat space, geometrically engineer this theory, and then translate this to the ADS5, S5. So there is some orbifolding involved. There is a worldsheet parity and the fermion number projection. So again, I'm not going to go into details. This is not. We actually didn't apply that so far, this knowledge, but one could make it quite explicit what kind of identification of angles one needs in S5 to define this projection. For fundamentals, this geometric engineering involves putting n D3 branes, some number of D7 branes, and to balance D7 branes, one needs also a 7 plane. So there is orientifolding involved as well. And again, there is a particular orientifold which corresponds to this SU and FA theory. And similarly, again, there is essentially it's ADS5 S5 with some particular projection of S5. Similarly for SP2N with fundamentals here, this theory was actually discussed early on, back in '98. It was understood how to reproduce conformal anomaly, at least a conformal anomaly, in the using this intuition that you should have D3 branes plus D7 brane plus O7 plane, or that's particular projection of ADS5 is 5. So once we have fundamentals, there is open string sector, so that means the corrections goes as 1 over n in power odd number. And again, I don't have time to go into details, but it's important to keep in mind that once we have these identifolds, we also have cross-cup contributions. Not plus, once we have orientifold plane, we have cross-cups. Once we have fundamentals, that means there is D7 brane on which open strings can end. There's also boundaries. So you need to consider world sheets not only sphere with handles, but sphere with cross-cups, sphere with holes. So if we want to compute free energy, we essentially want to compute string partition function on ADS5 with this on ADS5 with project S5, including all these topologies. So depending on theory, you want to look at particular topology. So let's start with simplest guess that say the free energy should be given just by effective action of some sort of type 2B theory with all sorts of corrections. So at free energy, at tree level, it should be just R4 type correction, and then there are one loop corrections. Say in orbifold theory, there will be R4 one loop. And one could ask whether this can give us what we actually get from localization matrix model. So I already discussed that story, so the story which in n equal 4, but let's look at, say, orbifold theory. So the result in orbifold theory, again, starts with leading correction is lambda 1/2. So that coefficient can be understood from projection, the volume, counting the volume, shifting n. But the interest is this lambda 1/2. And here we don't have a good idea apart from the fact that if you just look at R4 term, there is, in type 2B theory, there is R4 correction, 1 over alpha prime. And just on dimensional grounds, if you imagine evaluating this on ADS5 S5, that will give us precisely the scale, which is L squared over alpha prime, and that gives lambda 1/2. So it looks like one loop term should give us free energy, which scales as lambda 1/2. But the puzzle is that this one loop R4 term is exactly the same as tree level R4. And tree level R4 evaluated on ADS5 S5 should be absent because we don't have any correction at order n squared, at leading order. So it doesn't seem to be the right explanation. And furthermore, if we evaluate R4 on ADS5 S5, the S5 is projected, but ADS5 is unchanged. So R4 will just give us volume of ADS5 back. So from the volume of space, you just get volume of ADS5. It's still extended in ADS5. And that will give us, by that logic of cutoff, logarithm from the volume of ADS5. But there's no log in front of this square root of lambda. So it's not clear how to get this lambda 1/2. So it most likely comes from torus contribution, not effective action. One should not use this intuition that partition function is given by effective action. Anyway, I don't have much time to say anything about FA theory. So again, there's more a question how we're going to understand matching to string theory. The important point is that here we need to keep track of this or the n corrections, and indeed there is a way to understand this log lambda correction coming or the n from the effective action point of view. It's essentially similar to what happens for conformal anomaly. How much time I have?
You're good. 20 minutes.
Okay, very good. So just to take a few remarks to take of this out of this discussion is that once we are dealing with theories with fundamentals, there should be order n terms, and that intuitively interpretation is that there is a D3 brane, large number of D3 branes and small number of D7 branes regionally. But that's kind of intuition from flat space, but in ADS5 S5, you're just dealing with some particular projection of the theory. So that's all the n terms. And exponential corrections, in principle, may have interpretation of world sheet instantons. A reason for that is that once we have some projection of S5, there could be wrappings on S2 which are non-contractible due to orbifolding. So in principle, that could be interpretation of these non-perturbative exponential corrections. The exponential corrections are the ones which I mentioned when I discussed this SP2N theory. They just come from the expansion of this Bessel. You naturally get terms like this without any I. In this case, this is all the N term. This series is barrel summable. It's just this integral. So so that's different from these 1/n squared corrections. Unfortunately, everything is mixed up here. So just to summarize this part of what I just talked about. So some comments and open questions. So there is a lot of interesting data about strong coupling expansion. It comes from localization. And it looks kind of organized the way so that it should match to string theory. It is quite surprising. If you just look at the starting points, it's not clear why it should have this particular 1/√λ expansion. So, and we are not talking about planar limit now. We are talking about 1/n or 1/n squared corrections. So they are subleading. So it's definitely required to have better understanding of this analytic control. It's only very recently that it was understood how to work out these large lambda expansions, which I discussed. What remains to be done a lot of open questions is on string side, how to do simplest loop computation on string side beyond planar limit, beyond tree level. So now, what about the role of integrability? It plays no role at all in the discussion which I gave about localization. So localization is, matrix model is more or less just supersymmetry, but it may have some hidden role. A reason for that is, well, one circumstantial evidence is that there are very similar structures, these Bessel candles, appear in planar super-Young mills. I mentioned this octagon correlated. And in 1/n squared corrections in these n=2 models. So why that happens, we don't know, but these should be related to integrability, sort of, because this octagon construction was based on hexagon construction, which is sort of based on integrability. Now, the deeper reason could be that integrability actually controls the spectrum of strings, and when we compute loops, we glue the spectrum in. We use this spectrum to construct loops. So once we have correlators, it's less obvious, but say for free energy, it's just vacuum loops, so maybe integrability actually controls them in some way. So that's a very interesting question, but so far there is no good evidence. There is also twisted sector of orbifolding, which already is non-trivial at linear order n squared. And that raises the question whether these n=2 models are actually integrable, including twisted sector, already at planar limit. And maybe we'll hear something. Well, there was a talk by Eli Pomoni at Integrability Conference, and that I'm not sure that's related to that, but at least morally it's related to the question of integrability of n=2 models. So there's a very interesting question whether one could combine somehow integrability and localization. Then there is also a question about less supersymmetric orbifolds, and again, maybe integrability may have some consequences here. So now I switch to a different topic. Well, it's the same topic, but much more elementary, and which I kind of glossed over when I discussed the free energy of n=4. Namely, what's the value of type 2b supergravity action on ADS5-S5? So usually, if you look at papers that discuss application of ADS-CFT for this particular ADS5-S5 case, everything starts with this action in 5 dimensions. So we assume we compactify an S5 and we just write down 5-dimensional gravity plus cosmological constants. So essentially gauge supergravity, n=8 gauge supergravity action in 5 dimensions. So then if you pick up the ADS5 vacuum, you get volume. This action becomes a volume of ADS5. Now, if you introduce S4 as a boundary ADS5, regularized as we just discussed, you get this n squared. The volume with the cutoff, infrared cutoff, it just goes like this. So just to recall, the kappa 5 is related to volume of S5 and kappa 10, and the kappa 10 is related to string coupling, and the radius of ADS is related to string coupling. What did I do here? I think I have too much here. Yeah, either N or G string. Anyway, there is, yeah, these are volumes of, the important point is the volume of ADS5 goes as logarithm. So what, in fact, we get if we just start from 10-dimensional action. So if you look at 10-dimensional supergravity action, that's how it looks like, very familiar. So F5 is self-dual, but we don't impose this at the level of the action normally. We impose this condition on equation of motion. But what if we just take that action and evaluate it on ADS5? Clearly, we just get 0. F5 squared is 0, scalar is 0, and the action is trivially 0. So the bulk supergravity action on ADS5S5 is 0. So there's a paradox. How could it be that this action is 0 on ADS5S5, which is a vacuum, but 5-dimensional action is not? And it's a 5-dimensional action which is actually consistent with ADS-CFT. All sorts of applications to, say, black holes, etc., are all based on this action. And in some sense, it's kind of obvious that the two actions need not agree, you may think, because when we use some particular ansatz, like compactifying S5, substituting the action, and then it's not the same as going through equations of motion and reconstructing action for reduced number of variables. But the values of action on the full solutions, on the vacuum solutions, is actually still expected to match. And moreover, it's 10-dimensional action, which is fundamental. We should follow from string theory. So if you want to know about alpha prime coaction, we should start with 10-dimensional approach. We can't just go to 5 dimensions straightforwardly, unless we have systematic way to do that, but not through equation of motion. So one may think that this paradox is related to self-duality of F5, and in fact it's not quite right. The reason is that you can also consider, say, ADS3S3 with their three-form flux is self-dual, but there's no condition of self-duality on the three-form in the action. So it's not a question about writing action for self-dual field, it's rather property of a solution. So there also the action will vanish, 10-dimensional, 6-dimensional action will vanish, but 3-dimensional action will be not vanishing. So anyway, so the point of this story is that something is missing. And there's a particular boundary term which is missing, and it's not a Gibbons-Hawking-York term, and also not the terms which needed to make 5-dimensional action finite on solutions with AES5 asymptotic. It's something else, and in general, the general point is that one may, depending on which space vacuum one considers, one may need to add particular boundary topological terms to the bulk action. Flat space is one thing, ADS5 is another thing, and they may have different boundary terms which are relevant. For example, Gibbons-Hawking-York term is vanishing on ADS, but important for asymptotic flat conditions. So what we're going to do is to discuss that particular example when we have a topology of M5 times X5, where M5 is non-compact, X5 is compact. And that covers all sorts of solutions like ADS5, S5, D3 branes, and all that. So just to emphasize again, string effective action has a particular origin from, it's related to string partition function. And the fact that it vanishes on solutions has fundamental meaning. It's related to conformal invariance. So if you look at bosonic string and look at the bulk action of the bulk action is proportional to conformal anomaly. So Lagrangian, written like this, is proportional to conformal anomaly. So it vanishes once you have conformal invariance. So this conformal anomaly is written like this. So there's a dilaton boundary term which one needs to keep in mind, considering asymptotically flat conditions. But bulk term is vanishing. And in type 2B theory, an S and S part is the same, will be treated the same way, like in bosonic case. Ramon terms need more attention. So in particular, there will be, on equation of motion, there will be boundary terms coming, say, from F3 squared term. F5 is still squared, is 0 on shell, so here we definitely need something else to get non-zero value of the action. And what we need is a term like this. So we can We can't have F5 topological term, which is trivially 0 if you just interchange the numbers of fields, you get minus sign, and so it should be 0. But if you have topology like M5X5, for that particular topology, you can write a term like this. So you take essentially like electric and magnetic parts of F5 and take a product of them. And that boils down to compactifying on X5. That boils down to integral of F5 over 5-dimensional space, which is essentially a cosmological constant. It's just a volume form of the 5-dimensional space. Or that's equivalent form. So the suggestion is that we need to add this term with some particular coefficient a priori for that particular topology. So it could appear. And it doesn't change equation of motion. It's a total derivative, sort of, but you need to have such term a priori. So what is interesting, well, you need to fix particular coefficient gamma if you want to match this 5-dimensional reduced action. So this coefficient in front should be very special. And what this special coefficient is doing, actually, it's very simple. It's essentially reverses the sign of electric and magnetic parts in F5 squared. So on the usual self-dual solution, F5 squared is just 0. But if you reverse the sign, it will be non-zero, and that will be surviving. And remarkably, precisely that term, with that particular coefficient, also comes out of Pasti-Sorokin-Tanin formulation of 10-dimensional supergravity action. And there was a similar recent, somewhat similar reformulation of F5 self-duality of an action for type 2b supergravity, where self-duality is not imposed by hand but follows from equation of motion. It also leads to similar term. The bottom line is that I don't need to know about this self-duality problem, etc., etc. We just can argue that just on general grounds we may add extra topological terms in particular topological case. So that's the logic. How that follows from string theory, that's an open question. And here at the moment we're just at the level of supergravity. So in general, the bulk, the total action for particular asymptotic boundary conditions, this M5X5, it will have this topological term plus Gibbons-Hawking term a priori, the boundary term, and the total action will be the bulk plus topological plus boundary. So I just mentioned that this topological term essentially reduces to the volume form in 5 dimensions after we compactify on X5, which is, in the case of ADS5, S5 is just volume of 5 sphere. So we end up with precisely total action being just given by topological term, which is the volume of ADS5. So that generalizes to any X5, which could be any Einstein manifold. And that matches the prediction of ADS-CFT about the conformal anomaly coefficient. So usually we take some ADS 5 times X5 and ask what's the conformal anomaly in this case, and that produces this prefactor K, which is the ratio of volumes. And that will come out of this term as well. To further elaborate on this relation of this topological term and 5-dimensional reduced action, which I started with, again, that was my first slide of this part, was just this 5-dimensional action, which is reduced action with cosmological constant. So suppose we want to compare these actions more generally, namely 10-dimensional action for M5 times, say, S5 general ansatz and this 5-dimensional action. So we take 10-dimensional metric like 5-dimensional metric, some scalar nu, which is the kind of prefect of S5. And it's balanced so that there's no new prefect in the R term. And the 5 form can be kind of general with the condition that these are just volumes of the corresponding 5 space and S5. A in general is this coefficient is in general is a function still. And so this is kind of off shell. So what you'll get if you just compactify on S5 using this ansatz? You'll get R5 plus this scalar nu plus some potential. And that's how this potential will look like. So if you use equation of motion for this scalar A, these two terms cancel. and we do not get the right cosmological term constant in reduced theory. So that's the counterpart of the statement that if you start with 10-dimensional action, F5 squared is 0, so you don't getting the right action for the reduced theory if you just do naive reduction. But instead, if you use a 10-dimensional equation of motion and reconstruct 5-dimensional effective action, you get this potential. Instead of these 3 terms, you get 2 terms. And here I fixed B already 1, which is fixed by equation of motion. So what this potential is saying is that it has a minimum, and at the minimum, minimum is here is nu just nu equals 0. At the minimum, you get cosmological constant, precisely the one which is required in this reduced action. So this V tilde is the potential which comes out if you add this topological term. So if you start with bulk 10-dimensional action, add topological term, you get precisely this V tilde potential. And that matches, this kind of extends this 5-dimensional reduced action with just cosmological constant to the case when there are extra scalar nu, which is a excited radius of S5. So similar story can be repeated for other solutions, like D3 brane solution, full D3 brane solution with asymptotically flat region included in the harmonic function. So that's the expression. It has still M5, X5 topology, so it's easy to see why. So near the core, of course, we go back to ADS5, S5, but here the bulk action again for this solution is still 0. F5 squared is 0, and the scalar curvature is also 0. There's no dilaton here, so this is easy to see. But if you compute topological term, you just get precisely same as it happens that the Gibbons-Hawking-York term gives, yeah, I'm finishing soon, gives what it gives. It gives the integral of the along the volume of the worldsheet volume of D3 brane. That's these y coordinates. 4 y coordinates are the direction along the 3 brane. So just evaluating topological term gives the tension of 3 brane, or this prefactor, times this volume. And same comes from boundary term, in this case, where we have a asymptotically flat region. And total action is just this. So that is to say that the topological term contributes the same value as the Gibbons-Hawking term in this case. So the total action is just some number of D3 branes, tension of D3 brane, and world volume. And one can also add the source term, which produces this delta function with HR, and it also contributes the same. So the lesson is that topological term is as relevant as any other term, and you need to keep it in mind, otherwise you get wrong total value of the action, because the bulk term vanishes. So same can be repeated for non-extremal D3 brane, which is relevant for black hole thermodynamics, and also for composite solutions like smeared BPS intersection of D3 branes. In particular, we can consider intersection of 2 D3 branes, which near the core is the ADS3 S3T4. So it's kind of generalized ADS3 S3T4, or 4 D3 branes, which generalizes ADS2 S2 times T6. So I just flash this here. So for example, for 2 D3 brane intersections, that's how it looks like. And again, you have it no longer has naive this. You may say it still has M5 X5 topology, but here is not really. What is really relevant is that F5 doesn't have this decomposition. Instead, it has still electric plus magnetic decomposition. Electric means path with time direction, and magnetic is the complement to it. And the topological term still has the same form. So just you take electric path of C4, compute F5 electric, and compute this topological term. And it gives a result which is consistent with naive reduction, well, not naive reduction, but through equation of motion, reduction to 3 dimensions, where you get the value, which is just volume of ADS3. Same story for 4 D3 brane intersections, kind of look more messy, but again, there is electric potential, the electric field, magnetic is dual to it, and same story works out. So the same for ADS2, S2. So to conclude, so the message of this discussion is that depending on topology or asymptotic boundary conditions, different boundary terms can be relevant. And we knew that, say, for Gibbons-Hawking-York term, it's relevant for asymptotically flat, but it's not relevant for ADS boundary conditions. So similarly, there should be topological term if you want to have equivalence of the value of the action obtained through different routes, through equation of motion or from the bulk perspective. And that topological term has this structure. Now, what should I add? Similar terms can be added for other topologies. For example, for M3x3, you need to add this similar term for 3 forms. And M2x2 T6 similar term could be interpreted in terms of electric field in 4 dimensions, electric magnetic field in 4 dimensions, Maxwell theory. So we don't know what's the string origin of any boundary terms, in fact, and in particular this term. So that's an open question. Whether it can receive alpha prime corrections, it's unlikely, but still also open question. And how we are going to apply this logic to higher order terms, which I discussed in the first part of my talk, is another question. One final remark is that there is quite an interesting story about finite temperature contributions to free energy of n equal 4 theory, free energy at finite temperature. It's not the free energy which I discussed on S4, but rather on the circle times R3 or circle times some compact space. So here, alpha prime corrections are relevant, and they, in fact, by computer science, like R4 correction is relevant. But the value of the action, again, will depend on, possibly depend on this boundary term. So that's also another open question. So I guess I stop here. Thank you very much.
Thank you very much, Arkady, for the nice talk. Any questions? Right, Ellie has a question. Maybe Khalil, can you?
The last 2 points that you just made, the finite temperature and the higher order correction. Can you say a little bit more about that?
No, here I was referring to our old paper with the Gapser and Klibanov about the following thing. You take D3 brane non-extremal, or knee-extremal, and you compute the action, and what do you get at leading order? You get free energy, or you can define entropy just from the value of the action, just like Gibbons and Hawking did. And you get a result that free energy scales n squared times power of whatever, T4, times the volume. So then there are corrections to that formula, which come from alpha prime, and they come from R4. And the leading correction goes as zeta 3 over lambda in power 3 halves, and that's alpha prime cube. So that value was obtained, and even the first leading term was obtained by starting with 5-dimensional action. What I'm saying is that this needs to be rethought if you want to start with 10-dimensional action. So the result is correct, but the way how this should follow from 10-dimensional, that.
If I want to think that I want to compute the Wilson loop, I want to compute corrections at finite temperature.
Wilson loop?
Yeah.
Why Wilson loop? Oh, Wilson loop is a different story. Yeah, I had in mind just simplest free energy or entropy.
But is it clear to you what would be the leading, would that be the leading?
Leading to Wilson loop? You
Yes,
want to
yes,
consider
yes.
what?
If I have the 10-dimensional perspective now.
If I have 10-dimensional perspective, and why Wilson loop? Because of S1, because of temperature, why?
Just because it's an S observable.
Yeah, well, yeah, that will be a different story. Yeah, but regarding Wilson loops, in the previous story, there is a story about Wilson loops for n equal 2, but I guess you're not asking about that. You're asking about.
I mean both.
Both. Yeah. Okay. So for n equal 2 models, first for n equal 4 theory, there is a Wilson loop observable. So free energy looks kind of trivial, well, simple, like log lambda for n equal 4 theory. But Wilson loop story is more interesting in a way that, as was found by Gross and Drucker, it's given by circular Wilson loop, is given by some Laguerre polynomial as function of n and lambda. So it's more complicated than a non-trivial formula. And for n equal 2 models, the leading 1 over n squared correction for Wilson loop is actually determined by free energy. It's some derivative of free energy. So once we know free energy, we actually can compute also correction to Wilson loop. But in principle, this is also an interesting question, how we reproduce that on string side. Because reproducing Wilson loop and free energy is completely it's kind of phrased differently on string side. You look at minimal surfaces, the corrections to minimal surfaces, while here we look at just some closed string partition function. So in principle, it's kind of, the question is very relevant, and from string side, these are two very different observables. From localization, they're kind of related, because they can compute it in a similar way.
Any further questions? All right.
Thanks. I lost the ADS3 S3 story. So you say that for ADS3 S3 you need to add on the F3. F3
yeah,
term?
you may ask what about H3? Yeah, you may also worry about H3.
But
H3.
also earlier on you were talking about the D-brain action that leads to ADS3 S3, and it seemed to you seem to.
What?
This one here.
Yes.
And there you seem to not need the F3 term.
Yes, because, well, if you look at your latest paper, you know that this background can be supported by different fluxes.
So you say, oh. Yeah.
So this particular case is the case where you have just F5. So this particular space can be supported just by combination of F5. It comes out of this limit, yeah. Is it the right slide? Yeah, that's the right slide. Yeah, so if you just take that background and consider near horizon limit, drop this one, you will get geometry which is ADS3 S3 times T4, but the flux is just a 5 flux.
So you say that you would generate the new boundary terms by S-duality or something?
Yes,
right?
yes. So in principle, these boundary terms should be related.
So if you impose S-duality invariance on the boundary terms,
S-duality, well, S-duality just maps this to itself.
No, I mean if you take your boundary term F5 for F5 and demand...
Here you will need, to generate the other fluxes, you will need to do whatever, T-dualities as well.
T-duality, okay.
U-dualities, yes. T-dualities, yeah.
Okay.
Any further questions? If not, I have a quick question. So is there some sort of first principle that fixes these topological terms that you have to add, that you could have known before realizing there was a paradox, that you should have added them? Or
well, I mentioned this, in principle, you can change perspective completely and start with some whatever democratic formulation of fluxes and plus formulation where self-duality doesn't is not imposed at the level of the action, and ask what you actually get there. And this in PST formulation turns out that if you demand under some assumptions gauge invariance, you need to write the action in such a way that this term is there automatically. And moreover, in this other formulation, looks like there's a way to write this as if you don't know which background you're considering. It just turns out that in that background it will be non-zero, on the other background it will be zero. So that kind of logic. So yes, a priori I would say it's an open question. It's somewhat, well, logic may be different in different cases. Like in Gibbons-Hawking, you look at derivatives and it's different perspective. But here it looks like it's a different principle which you are requiring.
Okay.
Yeah, I think this is the best I can answer at the moment.
Okay, thank you. Okay, let's quickly thank Arkady once again.